Okay, welcome back. Um, so in this part of the class, I'm going to give you a live demonstration of MoT. So we'll take the same example I've shown you in the lecture, the open tank model, and we'll try to model it in MoT. And then we'll follow all the steps I showed you, like the problem definition, and the model and the variable analysis, and the solution for the same. And I'll also show you some other options which we did discuss in the lecture, and how those other options can be used in future projects or future assignments. Okay, so first I'm going to show you how to the installation procedure of the tool itself. Okay, so this MOT is a part of a whole software package which we call it as ICAS. Okay, so for accessing MOT you need to first install the whole ICAS, and you can get the installer for this ICAS along with the key from Professor Shichen. Okay, so this is how the installer look like, and this is the serial key. Okay, so I just double click on it to initiate the installation procedure, and this is how the first form would gonna look like. Okay, and just click next, and these are the terms and conditions, and you can just agree, and then in the next form it's gonna ask you the license key. So you can just open the license key here, which will be given to you, and then you should punch in the license key digits in that. So once you've done that, you can click next, and I would suggest you to not change any settings but to install the whole package, so that we can make sure it's consistent and it's working properly. Okay, so this is just the location where you want to install, it doesn't matter, but yeah. So then you can just click install, and it will do a silent install, and it will hardly take around 1 minute to install everything. Just give some time. So don't worry, at the end, exactly at the rear end, when it's trying to install this GTK runtime, it will take slightly more time, because this is kind of an external application which is added into the software package. So don't worry if it is a bit slow at the rear end of the installation program. Okay. So I mean, as I told, ICAS is an whole software package. So this is entirely developed at the Technical University of Denmark, and then the chief architect was Professor Kulkarni and his researchers under him. They have developed different modules in ICAS, different researcher groups under him. So and then they try to keep everything under one package, and they call it as ICAS. I think ICAS stands for Integrated Computer Aided System, ICAS, ICAS. And MOT is just one part of it, only for modeling, which is only used for modeling. Okay. So now you can see that it is completed, and here I would strongly recommend all the students to reboot your computer to just make sure that all the registries are done exactly the way it should have been done. Okay, so just for the continuity of the video, I'm not doing it, but then I would strongly recommend all others to reboot your system. Okay, so finish it, and then so in order to open the MoT, first you need to open ICAS. You just type in ICAS, or for that sake it will also create an shortcut on the desktop. It did create a shortcut, but then it will be in your programs files under ICAS, and this is the icon it's gonna look like, and you just click on it and it will open ICAS for you. So first of all, you will see a task manager when you open ICAS, and go for the third one, which is called MoT frame, which is the modeling framework. Okay, once you click the MoT frame, you will see MoT here. Now you can click on MoT and it will open this test bed, and here you just click OK, and then you can see the whole test bed here. Now all the work, all the modeling development would be done under this one. Okay, so first you try to save this application. Let's say this is example 1. I'll be saving it on the desktop, and now for the first step is the development of the model. So first we'll go to the view original model, and here we will type in all the equations. Okay, so here we will be solving the same example I've shown earlier, we have discussed in the lecture. So this is just the open tank model where the flow is characterized by pressure. We have seen that it has 4 equations, right? So I will just punch in all the equations exactly how we generally write on a piece of paper, or even in a text editor. Okay, so you can just go through. And one other important thing here is, if you want to comment anything, you just need to use a hash symbol at the beginning of the line, and then the whole line is counted as a comment. So I'm going to delete this one. Okay, I'm going to say this is a dynamic tank model. Okay, and this one. Okay, so I will start typing in the equations here. So first I'm going to write the equations for the pressure in the tank, which I gave it as P2, right? So P2 is equals to the atmospheric pressure plus the potential energy inside, which is given by R, which is the density, multiplied by the gravitational force, the gravitational acceleration, multiplied by the height of the liquid in the tank, and divided by this is just a small factor for the units. Okay, so now we have written the equation for P2. Now I'm going to write the equation for the flow, inlet flow Fin, and also for the outlet flow. So Fin is given by the equation Cv, which is the coefficient of velocity, multiplied by square root of P1, which is the pressure at the inlet, minus the pressure of the system or the tank here. Similarly, the equation for the outlet flow would be the coefficient of velocity multiplied by square root of the pressure difference, which is, in this case, it's P2 minus P3. Okay, so, and finally the height the height of the liquid inside the tank is how is it related to your flow rates. So I'll say so dH equals to F in minus F out divided by the cross-sectional area of the tank. So after punching in all your equations in this text editor, okay, I would highly recommend you to click the save button so that all the equations or all the work so far you have done is saved into the example file or to the file which you have given the name earlier. Okay, once you have done this, once all the equations are done, click here to accept changes. What it does is, like as I told you in the lecture, it will try to translate it to the language which is understood by MoT. Okay, so you just click accept, and here when you click accept, it will show you different options about compounds like the chemical species. Here you don't need to select anything, you just choose the first one. You just say that there are no compounds in the model. So because MoT also is linked with the chemical database, and if at all if you want to take some properties, it gives a direct link to the properties, so which is of no use for you here. So you just say that okay, there are no chemical compounds in the model. Okay, so once this is done, it automatically shows you the translated model. So if you open this, you can see how it is being translated into the language which is understood by MoT. Okay, so this is the translated model, and then there are other options like import model. For example, if all the equations are already in the text format, you can directly import it by clicking here and then just showing the location of the text file where they are, in which the equations are there, and it will automatically translate it and show you the translated form of the whole model. Okay, so and then if you want to modify the model, you can just modify it, but whenever you have modified, you should accept changes here, or else it will not be translated or it will not be updated. Okay, so and in the morning I showed you where you can give the iterators for examples. If you want to use an array of parameters, so this is where you need to use it. You can add an index relation, or you can edit an index relation, or you can delete an index relationship. Okay, so you just need to select here and say edit. You can choose what is the starting value and the final value, and based upon which the size of the array is taken. Or if you want, you can also add a entirely new index relationship. You can give your own name and the starting value and the final value. Okay, so since in this problem we don't require any iterator, I'm not giving anything here. Okay, but remember one thing: if you have an iterator, I would first say you should define the relationships and then you should write the model. Okay, so now that the model construction or the model definition is done, the next part is the model analysis here. So in the model analysis, first thing is to classify the variables, right? So as I told initially, so all the variables present in the equations it will directly take as parameters initially. So you can see that all the ones are taken as parameters here. So now we need to segregate or kind of differentiate all these variables into the respective classification. So here I'm going to choose the gravitational constant and the atmospheric pressure as parameters, and let's say the density is a known value, and h, which is the height of the liquid, is a dependent variable, right? So let's say the Cv, which is the coefficient, is a known variable, and P1 and P3 is also known, which are nothing but the pressure and also the cross-sectional area of the tank. Remember one thing here, that shows the explicit variables separately. It will not add that into the main variables list. Okay, And you can also see the incidence matrix here. And if you want to see what are the variables here, you can see it, and the equations they are present, you can see on your left hand side. Okay, so this is the incidence matrix, and if you're not comfortable with this color coordination, you can also uh, have these options where you can change the color of a particular classification of a variable. Okay, so for now I'm going to keep it this way. Now you have defined the model equations, you have classified the variables, and the next one is relating your your dependent variable and your dependent prime. So here in our problem, the dependent variable is the height of the liquid, and the dependent prime is the dH in the equations, right? So once you have done that, you have already completed your model analysis part, or sorry, your classification of variables and part completely. So now we need to set the variable values. So here you should give the parameter values and also the known variables list. So here I'm gonna give you the same information. So the first variable here is RO, which is the density. I'm gonna choose as the normal water, and the value would be 1000. And the coefficient of velocity is close to 34.325. Let's say, and the pressure at the inlet, let's say it's 2 atmospheres, and the pressure at the outlet, let's say it's around 1.5 atmospheres, and the area is, let's say, around 15 meters square. Now the atmospheric pressure acting, let's say it is just 1 atmosphere, and the gravitational acceleration is 9.81 meters square, let's say. Okay, so these are the variable values which I want to give for the for my model. Okay, now that you have completed, you should go, there are 3 tabs here. You should go to the second tab and then go to the model solution. Here is where there are the options which are related to solving the model. Okay, at this point I would like all the students to save your work, just to make sure that nothing happens during the solving procedure and you will not lose any of your model or model information. Okay, so the first one is the variable chart tree. So what it does is, like, if you want to see how a variable is changed during the solution process, or during the time during the different time steps in the simulation, you should actually select it here. So what I want to see is, like, I want to see how H is changing, and also I want to see how my inlet and outlet flow rates are changing with time. Okay, so once I've selected all the variables here, I will hit save. Okay, and then the next one is the solver options. Here I would ask the users to directly go to this one which says solve with output. Okay, so if you click it, it will show you different options. So the algebraic options are here, and if you are looking at the dynamic options, the kind of solver, you can see that it's automatically selected the solver, the integration options, etc. Here, please make a note about the time. It says that it's trying to simulate till 61 time steps, and the end time is 1. Okay, let's try to solve with this time. Okay, so yeah, I tried to solve it, and you can see that the height is still increasing. It has not reached to a steady state. It can be also reflected in both F in and F out, right? So what I'm going to do is, I will not see the result, but then I'll try to run to a greater time period and see whether the system is kind of attaining a steady state or not. Okay, so I'm gonna go till, let's say, 10 seconds here, and I'll try to solve, and you can see and you can see that it is moving to a steady state, but then it's not completely has reached the steady state. So I would say I'm gonna increase my timestamp to, let's say, let's say I'm gonna give 30 seconds. So yeah, now it looks like it has reached the steady state. So the final height inside the tank was around 7.5 or 7.8 or 7.7 meters, and then my inlet flow was stabilized till around 17, and my F out is also would be around the same. Then only it will be at a steady state, right? Here, as you can see, you can make a combined that of all the three, or you can just choose which one you want to see, and you can just add it, and then you can see different how the variables are behaving with respect to the time steps. Okay, so now I'm gonna close this one, and then you could see the main model solution. It says it will give you different options, but then here the results button, if you just click on the results button, you could actually see the final result of the height in the tank. But then if you want to see all the parameters or all the variables present, you can actually click on here and you can see. So here the final pressure P2, the steady state pressure, was close to 1.75 atmosphere, and yeah, the final height was around 7.745 meters, and then the input flow rate was around 17.166. Okay, and that would be the same as the F output also. Okay, so this is a very simple example where I try to write the equations and kind of try to classify the variables and show you the solution procedure. Okay, so as I told you, this is when you try to solve and the whole model and it directly goes to the output. But as I told in the morning in the previous class, that there is a step solve model. So for example, in this you have 4 equations, right? In time step 1, if you want to see what is the output of this equation, you could actually do that. For example, you just go ahead and press this button and you should try to evaluate. So in the first time step 1, it has calculated the P2 as 1. This is because the PATM, the atmospheric pressure, is 1 atmosphere, right? But RO is 1000, gravitational acceleration is 9.81, but your height, the initial height was set as 0. So that's the reason why the second term in the right hand side of the equation is 0. And then you are only left with PATM, which is 1. So that's the reason why P2 it is calculated as 1. Okay. So, and based upon that, my Fin, okay, is the same value as CV, I believe. Right, yeah. No, it's not the same value, but yeah, it is calculated by subtracting the P1, which was 2. Which was 2 minus 1, and it was 1, and then it's the square root of 1 into the CV value. Okay, so in the third equation, it has calculated it as 0. That is because your P2 is 1 and your P3 is 1.5, and you have got a negative value with respect to your square root, so which is an imaginary root, so that's the reason why it's a 0. Okay, so that is where you can try, that is how you can try to solve step by step. For each timestamp, you can see how the equation or what is the output of the equation, right? So that is all about the MOT here, and I would also like you to show some other options which are available. For example, if you want to run this model, but then if you want to do a multiple runs, where you want to change the parameter after a particular run and see how the system is behaving, whether it's reaching a steady state or not. So you can also do that in MoT. So here I'm going to specify that there are multiple runs, and for each run it's the same end time, it's 20 seconds, and then I'll say solve it. So it will ask you for the number of run to change parameters. Okay, so say do parameter changes on every run. Okay, then you can start your run. So this is the first run. Okay, now I'm going to close this one. Click OK. Oh sorry, I made a mistake. Let me do it again. So here, when you specify multiple runs and when you try to solve it, right, it will ask you the number of changes of parameter. So how many runs? Let's say I want to do it 4 times. Okay, so here this is the first where I try to run. Now wait a minute. Oh, sorry. I should give the number of runs here. Say I say I want to run the multiple times the same solution, one after the one, for 4 times, and I also want to change the parameters. Let's say 4 times. Okay, and say start running. So this is the first run. Now it says for the second run out of 4, what are the things you want to change? Whether you want to change the solver specifications or you want to change the parameter values. Okay, so I will say go to the parameter and say okay, my atmospheric pressure is not 1. Let's say my atmospheric pressure is 1.2, and now we can see how the system would behave. Okay, and it has already run, and you could actually see the solution here, where from the initial steady state was around 7.7 meters, right, as a height, and from there it has dropped. Now the new steady state value was right under 6 meters, right? So now I'll say for the current run my parameter is, let's say 1.5, or let's say 1.4. Now I'm gonna say okay, it has already run, and now you can see the result here. It has went all the way from right under 6 meters to the height has fallen all the way to just about 3.5, you can say. And you can also see how the F in and F out are changing. Okay, so now in the last run I'm gonna set it back to the original value of 1 atmosphere and see whether the system is going back to the original steady state or there is any bias in the system. Okay, so let's say okay, and now if you see the result, yes, it has gone all the way to the original steady state of 7.75, and this is where these multiple runs will be effective if you want to see how a system will react for any change of parameters or a change of particular variable in the system. So this will also give you some information on which variables will be set as just simple known variables or parameters. So if you want to run multiple runs with a particular variable, it is advised to make them as parameters. So as you can see, in multiple runs, only parameters are given a choice to change apart from the solver specifications. Okay, so that is all about MoT and other options. I will also show you some help files, and if you have any questions on the syntaxes or kind of operators this has, how to search for it or kind of thing, I will show you that. So I close this one, click OK, and then go to this help menu, and then there are a lot of things. First of all, I would say go with the manual. Okay, so here there are kind of examples on how to do it, like the model definition, some syntax rules, okay, which you can use and see. You can go through them, but then if you want any specific operator, if they're present in MoT or not, I would suggest you to go to the syntax, which will give you all the information about various syntaxes available. For example, it will show you the operators list, the special operators, which is with respect to the parameters, sorry, the arrays, especially the arrays, and then logical test operators and the other mathematical functions available in MoT. Okay, and here you can also see some special functions which I've shown you in the lecture. So all these syntaxes are given here, so you can just use them in your model development. Okay, and these are properties. As I told you, there is an inbuilt compounds database to this MoT, right? So if you want to get some particular properties, you can directly link the compounds, and all you need to know is the variable name, and you can just use this variable name to get that particular property of the compounds, which is of no use for you. In general, I'm just giving you for information, so that if at all if you are working in future with any of these things, it's easy to get, let's say, molecular weight of a compound. Okay, yeah, these are also some other properties of compounds. Okay, so that's all with respect to MoT. And if you have any questions or anything on the later, you can just write to me or send me a message, and I'll try to reply you over email, or if it requires us to meet, we can just schedule a meeting based upon the time. Okay.